Hello everyone. In this session, we'll see numerical on stiffness matrix method. So we know that the stiffness matrix method is also known as displacement method and also equilibrium method. So in this method, the basic unknowns are displacement components of various joints. There's displacements, and in the stiffness matrix method, we are using to solve the final moments using slope deflection method. So we know in the earlier classes we'll already discuss the stiffness matrix method and the differences between the stiffness matrix method and flexibility matrix method. So now let us see one numerical on the stiffness matrix method. Yeah. Here the analyze the continuous beam as shown in figure by displacement method or stiffness method. So this is the given continuous beam. In this, one support is fixed support and the other support is roller support, and other support is also a roller support. Here this fixed support to support B means from A to B the length is 4 meters is given. On AB the load is uniformly distributed load. It is loaded with 60 kilonewton per meter. And coming to the BC, the length of BC is 3 meters is given. And here on BC, the point load is acting at a distance of 1.5 meters from C. And the load is 100 kilonewtons. Means that point load is acting at the center of the BC. So in stiffness matrix method, we know that first step is calculation of dKi. So in step 1, calculation of dKi. So how to calculate the dKi is nothing but degree of kinematic indeterminacy. In the calculation of degree of kinematic indeterminacy is based on the supports. For fixed support, 0. For roller support in general, 1 rotation and 1 axial deformation. 1 rotation and 1 axial deformation. But we have to neglect this axial deformation. Only consider these rotations. Then the decay of the given continuous beam is 1 rotation at A and rotation at B. There are 2 forces. So the dKi is equals to 2. Means here you can draw that this is the fixed support. On this beam at support B on this roller, this is 1 rotation. And here on second roller support, here also 1 rotation. Means these two are the coordinates. This is the first coordinate and this is the second coordinate. These two are the coordinates of the beam. Now the next step is calculation of fixed end moments. Calculation of fixed end moments. So in the calculation of fixed end moment, first you have to consider span AB, then span BC. So in span AB, just draw the fixed end diagram of this span AB. This is A and this is B. On this A to B, the load is UDL and the load is 60 kilonewton per meter and the total length is 4 meters is given. So here the fixed end moment means here from A to B and B to A like this. So here if suppose A to B means here the fixed end moment can be denoted by M bar AB from A to B. So we have the formula is minus WL square by 12 and the load is 60 and the length is 4 by 12. Here we'll get the fixed end moment of this AB is minus 80 kilonewton meter. The units are very important. Here the moment force into perpendicular distance, so kilonewton meter. And similarly calculate M bar BA. So here what is M bar BA is WL square by 12. The formula is same. Only the difference is the rotation direction. So the answer is plus 80 kilonewton per meter. Sorry, kilonewton meter. Okay, these are the fixed moment values for span AB. Now similarly consider span BC. So coming to the span BC, here also draw the span BC. On span BC, the point load is acting. This is span BC and the load is acting at the center, that is 100 kilonewton load, and the total length is 3 meters. Here this support is B and this one is C. Calculate M bar BC first. So what is M bar BC? Formula is minus WL by 8. So substitute here minus and the load is 100 and L is 3 meters by 8. Then we'll get M bar BC is minus 37.5 kilonewton meter. And M bar CB. So coming to the M bar CB, in this symmetrical loading, in place of M bar CB also will have the same formula, but the sign convention is different. That is positive WL by 8, means that answer is plus 37.5 kilonewton meter. So this is the calculation of fixed end moment. Now the second step is forces developed in the coordinate directions due to the given loads. That is step 2. Here step 2. The step 2 is forces calculation. Yes, here the forces developed in the coordinate directions due to the given loads means we know that the coordinates are two coordinates. One is the coordinate at B and one is coordinate at C. So this is first coordinate, means at B point, and this is second coordinate at C point. So here the forces developed means first force is developed at B point and second force is developed at C point. That can be denoted by P suffix 1L, means force on coordinate direction 1. Here how to define or how to develop this force is nothing but from B to A plus B to C. The fixed end moment of this B to A plus B to C. So already calculated this fixed end moment at B to A is, will get already that as 80 kilonewton meter, and coming to the fixed end moment between B to C is minus 37.5. So here we'll get the force on this P1L is equals 42.5 kilonewton meter. Similarly, calculate this P2L. So at C point only we have this C to B portion. So M bar C to B. So M bar CB is already calculated that as 37.5 kilonewton meter. So these are the forces developed in the coordinate directions due to these external loads. So this is step 2. And coming to the step 3. So in step 3, we have to find out stiffness matrix. So how to find out the stiffness matrix? For this, stiffness matrix. And the stiffness matrix, you can using the slope deflection equations to calculate this matrix. For this, in this calculation of stiffness matrix, so here we have the dk as 2. So here have to find out the stiffness matrix is K11, K12, K21 and K22. So for the calculation of K11, K21 and K12, K22, what is the first step is have to apply the unit displacement in coordinate direction 1, then we'll get K11 and K21. In second step, apply the unit displacement in coordinate direction 2, then we'll get K12 and K22. So, our first, I'm applying the unit displacement in coordinate direction 1. So, what is coordinate direction 1 is nothing but at B point. Here, I'm applying a unit displacement. This is unit means 1, means theta is equals to 1. So, due to this, here it is fixed support. So there is no deformation or deflection. After some portion, here it will be deflected like this. Coming to the up to this B point. After at B point also here like this, and here again this is fixed support. So the deformation is like this, and here this rotation is K11. Yes. So here the unit displacement in coordinate direction 1. So using the slope deflection equation, here you have to develop the coordinate directions 1 and 2. So from this, here at this B portion, the theta B is equals to 1. And A support is a fixed support and C support it is a rigid structure. So C support is also at the C and the slope is 0. So using the slope deflection equation, have to find out K11 and K21. So how to calculate this? What is K11 and K21 is nothing but here the K11 stands for the force at first coordinate direction when the displacement is also first coordinate direction. And K21 is nothing but here this is the K21. This K21 stands for the force at second coordinate direction when displacement is at first coordinate direction. So here you have to calculate this K11 and K21. So using this K11 from here to here and here to here, apply the slope deflection equation from here to here and here to here. So first suppose B to A portion. So we know the slope deflection equation. 2EI by length of B to A, that is 4, into theta A plus 2 times of theta B. There is no deflection, so the term is considered as 0. Plus, now 1 means from B to C. 2EI by length of BC. Here the length of BC is 3 meters and starts from here. So 2 theta B plus theta C. On this BC there is no deflection, so that 3 delta by L is 0. Now simplify this one. Here substitute this theta A and theta C is 0. This theta A is 0 and this theta C is also 0. 2A by 4 and 2 theta B. Theta B as 1. This is 1. So here 2A by 4, 2 means 4EI by 4 plus here also 2EI by 3 into 2 theta B means 4EI by 3. We'll get 7EI by 3. This is K11. Now calculate this at this portion. One more K21 means from only C to B means 2 EI by C to B, the length is 3 meters, and here theta B plus 2 theta C minus 3 delta by L is 0. So here theta C is 0 and theta B is 1. Means at this portion we are assuming that unit displacement in coordinate direction 1. That coordinate direction is at B. So theta is equals to, theta B is equals to 1. So here we'll get this as 2EI by 3. This is matrix K11 and K21. Next. So in the second, I have to assume the unit displacement in coordinate direction 2. So here, this is the diagram. Here, now you can assume this is also fixed. And at this C portion, have to apply the unit displacement, means theta is equals to 1. Here at this portion, that is second coordinate and second direction. And here this is K12. Now this is fixed. So here this is the deflection curve. So at this portion, on this case, theta C is equals to 1 and theta B is equals to 0 and theta A is also 0. These two are fixed. Means there is no deflection at that supports. This is the unit displacement in coordinate direction 2. Here calculate K12 and K22. K12 is nothing but only from B to C. So here 2EI by BC length is 3 and 2 theta B plus theta C minus 3 delta by L is 0. In this case theta B is 0. So here we'll get this as 2EI by 3. And similarly calculate K22. Here from C to B 2EI by 3 again, but the theta B plus 2 theta C minus 0. So here this as 0. Then we'll get K22 as 4EI by 3. So now here we'll get that stiffness matrix K11, K12, K21 and K22. So what is that stiffness matrix is K11, K12, K21, K22. Is K11 is calculated, that is 7EI by 3. So this is the stiffness matrix. Now step 4. Before going to start the step 4, here the final forces acting in the coordinates is 0 and 0. And coming to the step 4. In step 4, have to calculate the displacements. For displacements, we have to use stiffness matrix equation. What a stiffness matrix equation is, K into delta is equals to P minus PL. So here we know this stiffness matrix K, and the delta is, means delta 1 and delta 2, these two are the displacements, and these are the final forces at a 0, and P1L and P2L is already calculated. So just substitute all those values here. This is 7EI by 3 and the matrix is 2EI by 3 and here also 2EI by 3 and here this is 4 EI by 3. And the displacements are delta 1 and delta 2. And the final forces are 0 minus P1L is 42.5, and here this P2L is 37.5. After simplifying this, here E by 3 is common, and 7, 2, 2 and 4, delta 1, delta 2, and minus 42.5 minus 37.5, and then delta 1 and delta 2 is equals 3 by EI, and the inverse of this matrix into C minus 42.5 minus 37.5. Then do the inverse is 1 by AB minus BC and D minus B minus C and A. Simplify that one. Then we'll get delta 1 and delta 2. Here the delta 1 and delta 2. Delta 1, delta 2. 1 by EI is common. After simplification, here we'll get this one as 11.875 and here minus 22.188. So these are the displacements. Means delta 1 is nothing but displacement at coordinate 1, delta 2 is nothing but displacement at coordinate 2. At coordinate 1 is nothing but theta b. So theta b is minus 11.87 by EI and theta c is minus 22.188 by EI. We know that the theta a is 0 because that is a fixed support. In the question he is given the support as fixed. Now the last step, that is step 5. In step 5 have to calculate the final moments. So how to calculate the final moments means using the slope deflection equation. So to calculate the final moments, first on AB, MAB is equals to M bar AB plus, here we know that this is the slope deflection equation. MAB is equals to M bar AB plus 2 EI by L of AB, 2 theta A plus theta B minus 3 delta by L. Here MAB is final moment and M bar AB is fixed end moment. So substitute the values already calculated, this fixed end moment and theta A, theta B and deflection. So M bar AB is minus 80 and here 2 EI by LAB is 4 meters is given and theta A is 0 and deflection is also 0. There is no deflection. So theta B is minus 11.875 by EI. So here EI cancel. Then we'll get the final moment on AB is minus 85. Here this is minus 85.938 kilonewton meter. Similarly, calculate the final moment on BA. Here for BA, MBA is equals to M bar BA plus 2 EI by LBA, 2 theta B plus theta A minus 3 delta by L. Based on that formula, just substitute the values 80 plus 2 EI by that length of BA is 4 meters and 2 theta B means 2 times of theta B minus 11.875 by EI and 3 delta by L is 0. After simplification, here MBA is 68.130 kilonewton meter. Similarly, calculate on BC. First on MBC is equals to same formula, M bar BC plus 2EI by LBC, 2 theta B plus theta C minus 3 delta by L. Substitute in that formula. This is minus 37.5 plus 2EI by 3 and 2 theta B means here minus 11.875 by EI minus theta C is 22.188 by EI. After simplifying this equation, then we'll get the final moment of BC is minus 68.130 kilonewton meter. Similarly, MCB is M bar CB plus 2EI by LCB, 2 theta B plus 2 theta C. So after simplifying this one, then we'll get here 0 kilonewton meter. Yes, these are the final moments of the given beam, MAB, MBA, MBC and MCB. So here you can observe one thing, at joint B, this condition is satisfied. B2A is 68.130, B2C is minus 68.130. So here the condition is satisfied, and at the free end the moment is also 0. Means a solution is in correct way. So in the stiffness matrix method, in first step have to calculate the decay and fixed end moments. In step 2 calculate the forces. And in step 3 stiffness matrix. In step 4 calculation of displacements. In step 5 calculation of final end moments. Yes, this is the problem based on stiffness matrix method. Thank you.